Okay, Assalamualaikum and good afternoon to all my students. Uh, okay, this is our fifth class of our lecture. Uh, for Monday, it should be the laboratory session, but we still don't have the experiment yet before we uh, uh, before we get to the chapter 2 because most of the lab session are involving the chapter 1 and chapter 2. So before I say so, then we have the lecture session lah. Okay. Semua boleh dengar. Kalau tak boleh dengar, sila bagi tahu. Boleh dengar ke suara saya? Hello. Okay, boleh dengar Okay. This is the solution for example 1.2 that I gave to you before. Let me check who didn't do the classwork. Okay, there are still 6 students who do not post their answer. Arif Afan, Muhammad Daniel Arham, Hidayat Barakpah, Haris Hafiz, Afiq Hafiz, Shamil Nazri. Okay, for those students, make sure every task that I give to this class, you must do. If not, I cannot know who can catch up the lecture, who do not. Okay. Okay. Let's see someone's answer. I randomly pick Raziman Mahathir. Okay, final answer Raziman 3.925. 3.93. Okay, it's correct. But the efficiency is 25%. This is wrong. A 7.93 kilowatt for the absorb heat removal QL. Right, correct. But word in is incorrect. Okay, word net is also correct, but your efficiency is not correct because this equation you give to here is not the isentropic efficiency of the compressor. This is the thermal efficiency that you use in the Rankine cycle during your MEC 251. So this formula is totally wrong. The isentropic efficiency of the compressor should be like this. Okay. Okay, that's Raziman. I try to pick someone else. Kamil Hakimi. Okay, Kamil Hakimi, the final answer is 3.93. Yes, it's correct. Okay, isentropic efficiency is also correct. 93.9. Okay, word in and heat removal is also correct. Okay, nice. Naufal Yasmin Yahya. Okay, Yasmin. Oh, okay, nice. Everything is correct. So that's all for the example 1.2. This is not the graded assessment, which is there is no mark in your answers, but I need you to give me the answer, because from this I can know that you understood the our lesson or not. Okay, thank you to the all students that tried to solve this example 1.2, and make sure for this person, these students, 6 students of those, make sure next time you do the answer. You okay? Okay. So 6 students. Uh for those 25 students who turn in their answers, there are benefits for you. If markah awak nanti on the borderline, maybe between A to A minus. Okay, for the students who show the effort in the class, I will try to help you lah. To try, if you on the borderline, I will try to give uh, a few marks to get a better grade. Okay, but for those who do not show the effort in the class, I cannot help you. Okay, so I try to warning before. Make sure you do your best in this class. Okay. If you have any question, just let me know. Put your question in the live chat here. Okay, if you don't have any question, let's continue with our lecture. Okay. In our last class, we go through to the types of refrigeration cycle that already apply in the industry or our real life applications, right? Okay, so there are a few that we have learned, such as cascade, multi-stage, multi-purpose, liquefaction, and absorptions. Okay, these are just the example. Maybe there are so many more, but for our syllabus, we only learn about these 5 types of refrigeration. Okay, but uh, in previous semester, normally there are 2 types that you have to focus more. Those 2 are cascade and multi-stage. Okay, so for today I will show you how to solve the problems or calculations, how to analyze the cascade refrigeration system. Okay, let's revise back what we have learned in the last week. The cascade refrigeration systems consists more than 2 vapor compression system. It is basically you add up one ideal refrigeration and another ideal refrigeration cycle. So we have a cascade system here. Okay. Okay. So the example of the cascade system that consists of 2 vapor compression cycles is shown in this figure. Okay, we have system B and we have system A. So those 2 systems are connected with the heat exchanger here. So the heat removed from the system B will absorb by the system A here. Okay, and then normal cycle in vapor compressions occur, and finally the heat will be released or removed to the surrounding here. So if you have 3 or 4 or 5 or more, then you just add up, stack it, stack until the number of system that you want. Okay, so the analysis here is between the system, lower system, which is here is B. The heat is transferred to the A here, can be derived as this equation. Heat Q, symbol Q from B, is equal to heat QA here. If there is no heat loss between those systems. But for our analysis, we just assume it is perfect, it is ideal, so there is no heat loss to the surrounding between B to A. Okay, but in real life, sure, it will be the heat loss occur between B and A. Okay. Okay, so for our syllabus, we assume it is 100% heat transfer between B to A. And then from Q, we know the heat from 2 to 3 can be calculated or can be obtained by using this formula. Mass flow rate of B times to the enthalpy change between state 2 and state 3. So MB times H2 here minus H3. So this is what we got. Okay, and then heat from here, total heat, which is represented by the QB, will be absorbed by the system A here. So the heat obtained here can be heat absorbed here can be calculated by using this formula. Mass flow rate of A here times to the enthalpy change between state 8 and state 5. So where enthalpy 5 will be higher than enthalpy 8, so we use enthalpy 5 minus enthalpy 8. Okay, then we can rearrange the equation by dividing MB and MA, enthalpy H2 and H3 over H8 and H5 here, like this. So this form is not necessary to be remembered, but you make sure you remember this equation. Okay, and then you derive it by your own self to get this form. Okay, so let's try do the example here. Example 1.3. Okay, consider a two-stage cascade. Okay, so we know now this is the two-stage cascade. No, not 3, not 4, not 5. We have only 2 stages of cascades, means that we have A and B. Okay, refrigeration system operating between the pressure limits of 0.8 and 0.14 MPa. Okay, I'll give you, the first thing you have to do is you have to sketch or draw TS diagram like this. Okay, so we have saturation like this. Okay, now we have 3 line of pressure. Okay, because the limit means that the highest one is 0.8 MPa and the lowest one is 0.14 MPa. Okay, and then each stage operates on an ideal vapor compression. So the questions just assume that the vapor compression is ideal, so there is no isentropic efficiency in the compressor, and there is no pressure drop in the system. And refrigerant 134A as a working fluid. So just jot down R134. Yeah. Okay. Heat rejection from the lower cycle to the upper cycle takes place in an adiabatic counter flow heat exchanger. Okay. The most important information here is the term of adiabatic. Adiabatic means no heat loss. Okay, where both streams enter at about 0.2 MPa. So we have another line of pressure here, 0.32 MPa. So now we have three lines of pressure, 0.15, which is the lowest one, 0.32, the middle one, and the highest pressure line is 0.8 MPa. Okay, if the mass flow rate of the refrigerant through the upper cycle is 0.05 kilogram per second, okay, this mass flow rate, it says that it flows in the upper cycle, which is if we put here is B, here is A, so the mass flow rate for B is 0.05 because here is the upper cycle and here is the lower cycle. Okay, simple as that. So it is your own choice if you want to name the upper cycle is A and the lower cycle is B. It is your own choice. It is not compulsory to name B as the upper cycle or A as the lower cycle. Okay. Okay, so the question is, what is the mass flow rate of the refrigerant through the lower cycle? So the question is, they want the value of m dot of the lower cycle. I name in my TS diagram that the lower cycle is A, so my symbol for mass flow rate is MA. This is the question. MB, the rate of heat removal from the refrigerated space and the power input to the compressor. Okay, where is the heat removal from the refrigerated space happen in the system? Is between here and here. So we have to know the Q dot L and the power input to the compressor. So now we have consists of two systems, so we will have two compressors. So work dot net in, you should total up the work net work in A and work in B. Okay, so the final question is the coefficient of performance, so the COP. Okay, in our previous class before, the equation of COP, we have to calculate Q dot L over work net, right? So in this case, we have combination of two systems, so we have to get the value of work net in, which is the value of summation work in A plus work in B. Okay, so we will get the value of COP. Okay, so I copy this one, sorry. Okay, I put it here. Okay, let's continue with our problem solving here. Okay, the first step is you have to find the mass flow rate at the lower cycle, m dot a here. Okay. Okay, but before that, I will complete my TS diagram. This is the ideal vapor compression, so it will be like this, and there will be the compressor A, then it pass through the condenser here at A, and then it drops like this. Okay, so this is this state 1, state 2, state 3, and state 4. Okay, so state 1, 2, 3, and 4 happens in the cycle A, but we have another cycle. Put the green. Okay, another cycle for the system B. We also have another compressor here, and then pass through the condenser at B and go through the throttling valve of B and evaporator of B. So if here for the A we have 1, 2, 3, 4, and now we can name this one is 5, this one is 6, this one is 7, this one is 8. Okay. So the heat transferred between the state cycle A and state cycle B happens in the heat exchanger here. So before you forget, please write down the equation. Q at A will be transferred to Q dot B by assuming that there is no heat loss happen, because in the question has mentioned this is the adiabatic heat transfer. Okay, so from QA we transfer to the QB, 100% transferred. Okay, so you write down the equation m dot for A, QA happen between the 3 and 4, state 3 and state 4. So enthalpy 3 minus enthalpy 4. And for the QB, m dot B is between the state 6 and state 5. So H6 minus H5. Okay, this is the equation for the heat transfer occurs between A and B. Okay, just highlight this equation. Make sure you do not forget. Okay, then as usual we have to find state 1, state 2. Okay, I put here state 2. State 3, state 4, state 5, state 6, state 7, and finally state 8. Okay, at the state 1, H1 approximately equal to H4. Okay, if you kalau awak perasan, saya namakan state 1 dekat sini kan. Okay, differently sebelum ni kita letak state 1 dekat sini. Okay, tak ada masalah. Nama ni tak ada masalah. This is just the symbol. This is just the name. You yang namakan dia state berapa-berapa. Tapi make sure awak consistent. Dan awak ingat, awak perasan. Macam tu lah. Sekarang ni saya sengaja letak state 1 dekat sini. Sebab nak bagi faham. Jangan awak hafal H3 minus H4. Tak. Awak kena faham. Bukan H3 minus H4. Sebab nanti kalau berubah nombor state ni, awak kena ingat yang kat sini tolak dekat dengan yang sini. Bukan, kalau nanti saya sini jadi namakan 2, 2 tolak 3. Kalau sini saya namakan 5, sini 6, so 5 tolak 6. So jangan hafal number ni. Hafal dekat mana berlaku tu. Faham konsep. Okay. So dari segi sini state 1 ni adalah H1 equal to H2. Okay, pressure dekat state 1 adalah pressure paling bawah kan. So kita nak P1 sama dengan 0.14. Okay, state 2. Okay, yang ni set vapor, saturated vapor. So yang ni pun P2 masih lagi sama dengan P1 kan, 0.14 MPa. So H2, okay, straightforward. You can get the value of H2 equal to Hg at 0.14 MPa. Okay, find in the table. Find the value in the table, properties table. Okay, and state 3. Okay, state 3 from the TS diagram already shown that this is the superheated. Superheated. Okay, and then P3 Okay, dekat tengah-tengah ni. Line tengah. So, dia adalah 0.32 MPa. Ikut soalan bagi. And then S3, okay, supposedly equal to S2, entropy. Sebab apa? Okay, sebab dia tak cakap, ni adalah ideal vapor compression. So, we assume that there is 100% isentropic efficiency. Okay. Dan daripada nilai ni, so kita akan cari nilai H3. Okay. Okay, dekat state 4 pula. State 4 kita tahu dia saturated liquid. Dan P4 pun masih lagi 0.32. Okay. So H4 awak kena cari dekat HF at 0.32. Okay. Bila dapat H4 akan dapat H1. Cantik. And then state 5. Ni dekat state, ni dekat saya tanda lah. Nak bezakan A dengan B. Okay, ni dah habis. Okay, yang atas ni A, yang bawah ni B. Okay. Okay, state 5. Sekejap. Tak warna lain lah pula. Warna apa? Warna merah. Okay, state 5. Dekat sini. H5 equal to H8. And then P5 still 0.32 MPa. Because it also happened on the middle pressure line here. 0.32 MPa. Okay. So for the state 6 we know similar to the state 2 here. So it will be saturated vapor. Okay. So P6 still 0.32 MPa. And then H6, okay, you can get the value directly from the Hg at 0.32 MPa. Okay, then finally we'll get the H6. Because our objective to get the value of enthalpy, and then from the value of enthalpy we will use in our formula here to get the MA, QL, work net, and COP. Okay, for the state 7 we know it will be the superheated. Okay, here outside the saturation region here, so it is superheated here. And then similar to the state 3, because state 7 is the exit of the compressor outlet. So state 7, P7 is the highest at the highest pressure line here, 0.8 MPa. And then entropy 7 will be similar values to the S6 because it is the isentropic process. Isentropic process happens in the mechanical device such as compressor, pump, or turbine. So in this question, it says that it is the ideal compression cycle, a vapor compression cycle. So we can assume that isentropic process is 100%, and then S7 will be equal to the S6 value. And then from this information, we have to find H7s. And finally, for the state 8, P8 still 0.8 MPa because it is located at the highest pressure line, and it states is saturated liquid. Okey, Assalamualaikum. Kita sambung balik. Tadi saya dah suruh kira entalfi kan. Okey, saya dah letak senarai entalfi yang saya kira. Okey, ni list senarai dia. Dan awak compare lah dengan nilai yang awak dapat. Kalau lain, sila bagi tahu, tanya soalan dekat saya. Okey, sebab H1, H2, H3 ni mungkin akan berbeza dengan awak. Dia mengikut kepada cara awak letak simbol dekat dalam TS diagram ni. Contoh kalau awak letak 1 dekat sini, so dia akan jadi berbeza lah. Tapi nilai tu masih lagi sama sepatutnya. Okay. Okay, jadi sekarang ni kita dah ada nilai entalfi. So we can proceed with our question here, problem here. Dekat contoh A, dia nak M dot A. Okay. Tadi M dot A mana nak cari, dia dah bagi M dot B. So, cara nak cari M dot A hanya melalui cara ni je. Yang ada connection dengan M dot B hanya melalui rumus ni. Okay, so kita pakai rumus ni. H3 minus H4 equal to M dot B H5 minus H6. Okay, tadi betul lah saya nak letakkan B ni ke upper cycle. Sebab soalan pun dah cakap Yang upper cycle 0.05. So saya namakan atas ni B. Jadi yang ni lah nilai dia B. Kan 0.05. Okay. H5. Okay. 95.47. H6 251.88. Then M dot A, okay, this is the unknown variable. This is the one that we want to find the value. H3 255.93 minus H4 55.16. Okay, and then you will get M dot A. Okay, use your calculator. Okay, 0.05 times 95.47 minus 251.88 divide by, oh, sorry. This is not H5 minus H6, is H6 minus H5. Sorry, I did do the mistake here. Okay, 251. Okay, 47. Divide by 255.93 minus 55.16. And then you will get 0.039 kilogram per second. So this is the answer for question A. Okay, and then for B, Q dot L. Okay, Q dot L happens between the state. Okay, I use this between the state 1 and 2. So this happen here, Q dot L. So you have to find the value Q dot L by using the M dot A, because it happens in the lower cycle and also between the enthalpy H2 minus H1. Okay, MH2 minus H1. And straightforward, M dot A is the value that we obtained in the question A, 0.039 times to the enthalpy change of H2 and H1. 2939.16 minus H1, 55.16. And finally, we will get the value. Okay, so the unit here, kilogram per second times with the enthalpy, kilojoule per kilogram. So you will get the kilojoule per second. It's also equivalent to kilowatt. and we will get 7.176. The unit is kilowatt. Okay, and work net. Okay, work in total lah, sama juga dengan work net in. Okay, work in total lah, so awak kena kira dua-dua, work in dekat A plus work in dekat B. Okay, work in dekat A berlaku antara 3 dengan 2 kan. Work in dekat B berlaku dekat 7 dengan 6. So work in A sama dengan M dot A darab dengan yang ni 3 tolak 2. So H3 tolak H2. Okay, yang A. So kalau work in dekat B, M dot B, okay, berlaku antara 7 dengan 6. Okay, so rumus ni lah kita pakai. Aduh. Hai. Besar sikit. Okay. So pakai warna hijau lah pula. Okay, so M dot A tadi berapa nilai? 0.039. H3, tengok dalam list ni, 255.93. H2, 239.16. Okay, so awak akan dapat nilai tolak 239.16. So awak akan dapat 0.65403 kilowatt. This is the work in for A. Okay, for B. Okay, B tadi